My name is Amanda Stribe, and I'm going to talk about iterated decomposition of biased permutations. This paper is joint work with Sarah Meyerkel and Noah Stribe. In this talk, we're going to explore the decomposition method as a way to bound the spectral gap of Markov chains. We'll start with our main application, which is the problem of sampling biased permutations. We assume we're given a set of parameters, Pij, for all pairs I and j. And the nearest neighbor transposition, Markov chain M, operates as follows. You pick a neighboring pair of elements I and j. With probability 1/2, you do nothing. But otherwise, with probability Pij, you move I to the left of j. And with probability Pji, you put j to the left of I, regardless of what order they were in before. The Markov chain M is ergodic, which implies that it converges to a unique stationary distribution pi, and that distribution will depend on the set of Pij's that you have. The central question we're interested in is how long the convergence takes, which we call the mixing time. It turns out that we can get a pretty good answer by looking at the eigenvalues of the transition matrix P that defines the moves of the Markov chain. The mixing time is closely related to the spectral gap, which is the difference between the top two eigenvalues of the transition matrix P. So in other words, it's 1 minus the second largest eigenvalue. In particular, we want to know when the spectral gap is an inverse polynomial in n, because that implies that the mixing time will be a polynomial in n. And sometimes I may say that in this case, the chain is rapidly mixing. This Markov chain for permutations has been widely studied in both the uniform and the biased settings. In 2003, Jim Phil presented a set of monotonicity conditions on the Pij's, and he conjectured that they are sufficient for polynomial mixing. In fact, he conjectured that the worst case is the uniform distribution when the Pij's are all equal to 1/2. And in that case, the spectral gap is 1 over n cubed. He called this the gap problem. So this conjecture is still open. It's been verified for some classes of Pij, and the monotonicity conditions have been shown to be necessary. So here's just a list of a few results in this towards the conjecture. And recently, people have looked at a slightly simpler problem where there are k types of particles in a linear array. And all particles of types I and j interact with the same probability Pij, while particles within each class do not swap, so they stay in a fixed order. So you can write these just as their class number. When k equals n, this is the original permutations problem, but having this parameter k allows you to analyze the spectral gap in a new area. So if you set k equal to 3, Hadadun and Winkler proved that it was rapidly mixing in that case. And in previous work, we proved that it's rapidly mixing for all constant k. Okay, so I want to give an idea of how the analysis goes for some of these previous results because it lays the foundation for our strategy. So we're going to start with a case that was analyzed by Bhakta et al., where the Pij depends only on the smaller of I and j. And the idea is to decompose the transitions of the Markov chain into different sets depending on whether or not a 1 is involved. The idea would be that if all the 1s get to a random configuration and all of the particles of higher type are in a random order as well, then the overall chain should be mixed. So to formalize this idea, you can rewrite a k-particle system. So this A-B pair that we have here, we're going to write it as a pair AB. where A gives you the location of all of the ones, and B gives the relative order on all the larger particles. So I've laid out the elements of B so that they line up with the elements in the k-particle system, but the space doesn't mean anything when we're talking about B. It just tells you the relative order of those elements. The transitions that swap a 1 with something else in the k-particle system only change A, since they don't affect the relative order on larger particles. So if I swap this 1 with this 2, it doesn't change the order on B. It just changes this from a star to a 1. So we allow some extra transitions so that the particles within B can be swapped. For example, the 2 and this 2 and this 3 can be swapped across the 1 because we want it to be able to move and not get stuck. And we do that in such a way as to preserve the desired stationary distribution on pi. Okay, so this mapping I've defined is a bijection, so that if you're given A and B, we can reconstruct the k-particle system. Now, the special thing that Bhakta et al. Noticed is that in this case, the Markov chain restricted to moves on A is independent of the Markov chain restricted to the moves on B. So this is because the probability of swapping a 1 with a 2 is the same as the probability of swapping this 1 with a 3 if instead of having a 2 here we had a 3, because the probability of swapping I and j depends only on the smaller. So P13 is the same as P12. Okay, so in this case, the Markov chain is actually a direct product of the Markov chain that operates on B and the Markov chain that operates on A. Okay, so if you look at the direct product of two independent Markov chains, so here a row is labeled by A and a column is labeled by B, and for any AB, there's a unique element in here. And moreover, the probability of moving from AB to AB prime doesn't depend on A, for example. So if you have such a direct product, then the gap, the overall gap, is equal to the minimum of the gap for the row Markov chain and the gap for the column Markov chain. Okay, so you can use this. If you go back to this case, you can do an iterated analysis where you first analyze the gap for the ones. And what we showed was that the gap was 1 over n squared for the ones. And then you can fix the location of the ones and redefine A and B so that now A fixes the location. A moves the 2's around, and B has elements of higher order. And in that case, you also get 1 over n squared for the gap for A. And basically, you can repeat this procedure, and each time you get a bound of 1 over n squared on the gap, and because each of these is independent, you get a bound that's 1 over n squared overall. Okay, so you may notice that this 1 over n squared bound is better than the 1 over n cubed gap in the uniform bias case. And this is because we've assumed that the PIJs are bounded away from a half. So it's actually faster than it is in the uniform setting because the elements within a class are not swapping, remember, because we kept those in a fixed order. And the elements of different types have a bias, which actually makes the convergence faster. Okay, So this works great when the chains are independent, and we had that when the Pij's were equal to R sub I, so they only depended on the smaller of I and j. But this is not true in general, and in general for this problem, you can still write the Markov chain, you can still write the state space as a product space, so every element can be written as A comma B, but those probabilities are no longer independent. So the probability of going from AB to AB prime, now it depends on both A and B. Okay, so we're going to define restriction chains by discarding transitions that leave a given row or a given column. We call those, the column Markov chains, complementary restriction chains. And we'll just define this gamma min hat and gamma min tilde to be the minimum over the gaps of each row and the gaps of the columns. And what we want is that the overall gap should be close to the minimum of the minimums over all the rows and columns. That is what we would like. Unfortunately, that's definitely not true in general. So there are Markov chains that are rapidly mixing within each row and within each column, like the picture I've shown here, that still have this sort of bottleneck behavior where it's difficult, for example, to get from the top left corner to the bottom right corner. And this sort of bottleneck behavior is characteristic of exponential mixing time. So the classical way to get around this problem is to use the decomposition method, which was designed for this purpose. So we still have restriction chains, but those complementary restriction chains are replaced by a projection Markov chain, P bar. And of course, this theorem works in more generality than what I'm stating here, but bear with me. Right, so the decomposition theorem of Madras and Randall states that the overall gap is bounded by the product of the minimum over the restrictions times the gap of the projection chain. Okay, so this result is great, and it's been widely used to provide the first inverse polynomial bounds on the spectral gaps of a variety of Markov chains. And in fact, it is tight for some chains, but unfortunately, sometimes it is quite loose, such as in the case we're looking at where the direct product, like for example, if you have a direct product, then you would expect to get the minimum of the minimum gap with the projection gap instead of the product. Okay, so but in the absence of something else, we're going to use this decomposition theorem and see what happens when we apply this decomposition theorem to the permutations problem. Okay, so we assume there are k types of particles and we'll iteratively decompose k minus 1 times. And you can show that at every iteration, the projection chain is 1 over n squared, has a gap of 1 over n squared. And the base case also has a gap of 1 over n squared. But unfortunately, when you apply the decomposition theorem iteratively in this way, you pick up an extra factor of 1 over n squared each time you apply it. And so the bound that you end up getting, which we ended up getting, is 1 over, it's exponential in k. Okay, so unfortunately, this bound is only an inverse polynomial when k is constant. And we really would like to get close to 1 over n squared. And in order to do that, you would need a decomposition result that's much closer to the minimum, as I was saying. And This is definitely not true in general, but it seems reasonable in this application because for monotone distributions, the chains appear to be nearly independent in some way. So what we want is a new decomposition theorem that takes advantage of this fact. And just to drive the point home, getting these tight bounds is crucial when you're applying the decomposition theorem iteratively. So there has been a lot of work on improving the decomposition bounds over the years. And some of these results are even iterable. So the JSTV paper has some iterable bounds in it. We were not able to get these results to apply to our application. And so we decided we needed a new decomposition theorem that allows us to take advantage of the chains being nearly independent. But part of the challenge is to decide what it means to be nearly independent. And as we were thinking about this, we wanted to think of independence as a spectrum. And if somehow we could quantify how close we are to being independent, like we're closer to being a direct product than we are to this pathological case over here. And the way that we decided to do this is we quantified the degree of independence via this function R of AB. So the R of AB gives the joint probability divided by the product of the probabilities. So pi of A, it's a little bit of an abusive notation. It just means the sum over all of the AB pairs with that particular A. And if you had a direct product, then for all pairs A and B, this R of AB would be 1, right? Because the probability of AB is just the probability of being A times the probability of B. However, we're not going to require a pointwise bound on R. We're only requiring that R of AB is close to 1 on average, even if it can be exponentially large or small for some pairs A and B. And this is crucial for our application because sometimes R of AB can be very large or very small. It can be exponentially large or small. So what do we mean by R of AB being close to 1 on average? We define this quantity epsilon, which takes the weighted average over all pairs A and B. So we're weighting it by its probability of this quantity. So the square root of R of AB minus 1 over the square root of R of AB squared. So you can notice that if R of AB is 1, then this quantity is 0. And if R of AB is very large or very small, in either of those cases, this quantity is very large. So what we want is that epsilon should be close to 0. And that would mean that R of AB is close to 1 on average. We say a decomposition satisfying this equation is called epsilon orthogonal. Right, so this is a concrete quantity that we can bound, and it's combinatorial. It doesn't depend on the dynamics. It only depends on the stationary distribution pi. So that makes it a little bit easier to analyze. And then we prove that if the decomposition is epsilon orthogonal, then the gap satisfies this equation. So remember, this is the minimum of the rows and the columns, and we get this extra factor of 1 minus the square root of epsilon squared. So this bound, right, you want epsilon to be small so that 1 over epsilon is big, because in this way you can iterate it 1 over square root of epsilon times and only get a constant overhead. This theorem also generalizes to non-product spaces, but for ease of exposition, we didn't want to go into that here. And our result is similar to a result of Disdainville, but we think this introduction of the epsilon orthogonality condition is useful as a way to, we think it's an easier quantity to bound. Okay, and finally, we use the same techniques to prove a classical decomposition theorem. By classical, I mean it actually uses the projection chain, and it does generalize some theorems that have appeared earlier. Okay, so now we can use our new theorem to analyze the permutations problem. We show that as long as there are at least a logarithmic number of particles of each type, then the decomposition is 1 over n squared orthogonal at each level of the iteration. So we do need this extra condition that there are enough particles of each type, but then we can show that the chains are independent enough that we can iteratively apply decomposition, and we apply it order n times, and we still get a bound of 1 over n, on the order of 1 over n squared, which is optimal up to constants. Okay, so we can prove nearly optimal bounds for k as large as n over log n, where the previous best known bound was constant k. Just to sum up, we proved this new decomposition theorem, which we call complementary, and a classical decomposition theorem, and we applied it to the bias permutations problem, and we got optimal bounds up to constants. Thank you for your attention and for coming to my talk.